Okay, so let's talk about gravitation. So let's say we have an object which is mass m. So there is always the gravitational field exists on the surrounding of the mass m. So this is what we call gravitational field. Field. Okay. Okay. As the gravitational field exists on the surrounding of the object, so the mass m is always exert the gravitational field. So the gravitational field is always represent in terms of gravitational field lines. So this gravitational field lines is always pointing towards the mass of the object, pointing toward the center of the object. Sorry. So this one, okay, this one, this one, this one, and this one. So all the gravitational field lines is always pointing towards the center of the object. So this is what we call the gravitational field. So as okay, so let me draw this field to be wider. Okay. Okay, as this object exert gravitational fields, so this causes the object to become attractive. What is meant by attractive? It means that this object is able to attract another object which is from a far distance. So let's say we have another object. So this is our M1, this is our M2. So let's say this M2 is about to uh, enter the region of the object of M1. So this M2 is about to be attracted towards the direction of M1. This is because M2 is in the region of gravitational field of M1. Okay, but at the same time, this M2, okay, let me draw this wider. Okay. Okay, let me erase this one. Alright. So let me draw this wider. This means that M2 is inside the region of the gravitational field of M1. So at the same time, this M2 also exerts its own gravitational field. So this one is the gravitational field lines for M2, which is pointing towards the center of M2. Alright. So as M2 exerts its own gravitational field lines, it means that M2 is also able to attract M1 towards its direction. So so M2 is about to be attracted towards M1, and at the same time M1 is also to be attracted towards the direction of M2. So this attraction which is attraction towards each other, so this attraction is what we call gravitational force. Gravitational force, which is denoted as F. So F1, this one will be F2. So F1, as you can see that F1 is pointing towards this direction. This is because is always attractive. Okay, as for F2, F2 is always pointing toward this direction. Well, it means that M2 is also attractive. So as you can see that F1 and F2 are always in the opposite direction. So it means that F1 is actually equals to negative F2. Different value sorry, should be same magnitude but different direction. So this is how we determine the direction and direction of the force between two objects. So from this equation, we can know that this equation actually obeys Newton's third law. Newton's third law, which defines that gravitational force on M1 on M2 is actually equals to the gravitational force of N2 on M1, which is opposite direction. So this one will be opposite direction. Okay, so let's move to the next part. Okay, let me erase this one. Okay, this one as well. Okay, let's talk about the definition for gravitational force. So what is the actual definition for gravitational force? So based on Newton's law of universal gravitation, sorry, of universal gravitation, which defines that the gravitational attractive force is always directly proportional to the product of the two masses and inversely proportional to the square of distance between them. So square of distance between them. So this is how we define the definition for Newton's law of universal gravitation, which determine the gravitational attraction force. And this one should be attractive. Okay. Okay, this one should be attractive. So the gravitational attractive force is always directly proportional to the product of the two masses and inversely proportional to the square of distance between them. So this is the definition, and this is for the qualitative explanation. Okay, in terms of quantitative, okay, let me erase this one. Okay, in terms of quantitative, we represent the definition in terms of formula. So this is our gravitational force, which is directly proportional to the product of the two masses and inversely proportional to the square of distance between them. Okay, in terms of equation, so F is actually equals to negative G m1 m2 over r square. So this negative means that the direction of the two forces, which is equal, F1 and F2, as we mentioned just now, is always opposite direction. Opposite direction. Or we can say that the negative sign is actually equals to opposite direction of increasing r. Opposite direction of increasing r. R means the distance between two masses. Okay, so this negative sign is actually not necessary to be involved in the calculation. Okay, so this G is actually gravitational constant. Gravitational constant. So this is how we define the formula for the gravitational force. Okay, let's move to the next part. Okay, so let's move to the gravitational field strength. Gravitational field strength. So what is actually means the gravitational field strength? So we know that the weight of the object, which is F, is actually equals to mg. So okay, so this G is actually equals to F over m. So let's say okay, so this F is also actually equals to our gravitational force over r square. So have to note that our weight of the object, which is exerted on the mass of the object, should be the weight which is exerted by the object is actually equals to the gravitational force exerted by the object. So this F eventually it will be equals to our gmm over r square. So this divided by m, so this will be cancelled. So the final answer we got will be gm over r square. So this is our G. So in terms of qualitative explanation, gravitational field strength is actually defined as the force per unit mass acting on at that point, acting at a certain point. Okay, so this is the keywords here. The force per unit mass, which is gmm over r square divided by m. So this one will be our explanation for gravitational field strength. So, okay, this G is also well known as acceleration due to gravity. Acceleration due to gravity. So this is what we known as G. Alright, so let's move to the next part. So let's see how G varies with the distance. Okay, so let's say we have our Earth here. So this is our region of the gravitational field of the Earth. So this one will be our gravitational fields. Okay. Okay, so this is our region of gravitational field of the Earth. So let's say there is an object with the mass m is about to be attracted towards the center of the Earth, towards the direction of the Earth due to the gravitational field. Okay. Okay, so we need to know that how the gravitational acceleration, or well known as gravitational field strength, varies with r. So variation of G with r. Okay. So in terms of graph, so this is our y-axis. So this is our x-axis. Okay. So this is our r between the Earth and the mass. Okay. So this is our G. So our Gm over r square is here. So this is mass of the Earth. So this is r. So here, so this line represent the atmosphere of the Earth, which means that it is the radius of the Earth before we going out to the space. Okay, so our gravitational field strength inside the Earth is actually equals to negative 9.81 if the mass is about to approach the Earth. So so inside the Earth, as the mass is approaching the atmosphere of the Earth, so the gravitational field strength exerted by the mass is always negative 9.81 after the mass enter the atmosphere of the Earth. Okay. Okay. When the object is outside the Earth, it means here to, okay, from the surface of the Earth to until the mass of the object, so the gravitational field strength is always varies. Okay, let me draw this curve like this. Okay, it means that G outside, as for outside the Earth, G is always inversely proportional to the square of distance between the Earth and the mass. So this is how we represent the variation of the gravitational field strength and the distance between two objects. So this one, okay. Okay, so this is our curve here. Okay, so this is how we determine the relation between the G and R. So let's move to the next part. Okay, let's move to how. Okay, we're still in the parts of the variation of acceleration due to gravity, acceleration due to gravity, with distance, but this time is from the center of the Earth. Center of the Earth. Okay, just now we discussed about the object. The object is about to approach Earth. Now this time we are going to discuss about how acceleration due to gravity varies with the distance when the object is about to move away from the Earth against the gravitational pull. So this time is against gravitational pull. Gravitational pull. Alright, so we know that our acceleration due to gravity is gm over r squared. So this time when the object m is about to move away from the Earth, so this time negative is not required. This is because object is moving against gravity. So this is gm over r squared. So okay, so let me erase this one. Alright, okay, here. So let's say when the object is at the distance which is outside the Earth, r is greater than capital letter R, means that the object is already outside the Earth. Alright, so G is actually gm over r squared here, same as here. So the relation between G and R is actually G is inversely proportional to the square of distance between Earth and the mass, between the distance of the Earth and the mass. Okay, so this is for the distance which is outside the Earth. Alright, let me erase this one. Okay, let me erase this one as well. Alright, okay, as for when the object is still inside the Earth, which means that which means that this is our Earth. Our mass lies here. Is about to move away from the Earth, but still is inside the atmosphere of the Earth. So this is our R. So this is our small r. Okay. As for the distance, which is less than the radius of the Earth, so we know that g is actually equals to gm over r square. Okay, as we look on this figure, so we know that the mass m is still inside the Earth, so we know that the density of the Earth is actually equals to m over v. So the mass of the Earth is actually equals to the volume times the density of the Earth. So we can the volume of the Earth is actually 4 over 3 pi r cube, which is the formula for the sphere. Consider the Earth is totally sphere, times the density of the Earth. So we can directly substitute this one into the gravitational field strength formula. So 4 over 3 pi r cubes rho. So this one will be divided by r square. So this one cancel, this one will be only r. So the final answer we got will be g pi r rho. Okay, from here we can see that, let me write here. Okay, we can see that the relation of gravitational field strength of the Earth and the distance between the Earth and the object is always directly to the distance between the Earth and the mass of the object. Okay, so yeah, we can see that our gravitational field strength is always directly to the distance between the Earth and the mass of the object. So this is how we determine the gravitational field strength when mass is inside or outside the Earth. Okay, so let me erase this one. So how we represent this gravitational field strength, which is against the distance between Earth and the object, in terms of the graph. Okay, let me draw a graph here. So okay, this is our y-axis. Okay, so just now when the object is about to approach Earth, so the g is actually equals to negative. So this one is actually moved away from the Earth, so this g is actually equals to positive. So this g will be a positive value. Okay, so this one is our g and this one will be our r. So this one will be our inside of the Earth and this one will be outside. Okay, so we know that r, which is less than the radius of the Earth, which is e, is g is directly proportional to the distance. So as for r is more than the distance of the radius of the Earth, so we know that g is inversely proportional to the square of distance between the Earth and the object. Okay, so as we represent in this graph, So we will get straight line in this graph. Okay, so as for outside the earth, we got this curve, okay, which is until the infinity. So this is how we represent the graph between G and R. Okay, so let's move to the next part. Okay, so just now we discussed about the gravitational field strength, the variation of gravitational field strength with the distance of the Earth. So um, what about the variation of gravitational field strength? Gravitational field strength with the latitude. Okay, so this is the latitude. Okay, consider we have our Earth here. So this is our Earth. Okay, let me draw up all the component that is needed. Okay, this is our equal lines, which is lies in the middle of the Earth. Okay, so this is okay. So this is another line. Alright, so this is our radius too. Okay, so consider we have north, okay, we have east, we have south, and finally we have west. Okay, oops, okay, consider our mass is here. This is our mass m, so this is the degree here. Oops, so there is another line here. Okay, so this one will be here, and this one will be right here, and this one will be here. Okay, as we know that this okay, this will represent the weight of the object, which is mg, or well known as gravitational force, which is pointed directly towards the center of the circle. Okay, so as the mass lies at the degree of theta here, so okay, as the mass lies at the theta here, so this will be our radius. Okay, so this radius, okay, this one is the actual radius for the Earth. Okay, but the location for the mass m is actually r prime. Okay, we know that this line and these two lines is parallel, so this made an alternate angle for this between these two lines. So this one will be our alternate angle, which is angle here is same as angle here. So this made okay, how should I set? So this made an component for the r by saying that so this one will be our, so okay, let me draw another line so that you can see clearly. Oops, okay. So consider we draw these two lines. Okay. So this one, okay. Okay, here. So this is our theta here. So this is our r prime. Oh, let me just draw which is the same direction from that diagram. Okay, so this r prime is actually pointing towards here. Okay, so this will be our actual radius of the Earth. So this will be our r prime, so this one will be our r. So this is our radius, theta, sorry. So as you can see that from this diagram, we know that this line is actually represent the true radius of the Earth, which is r. So but the location of this mass m, we need to know that the distance here, the distance of mass m until the center of the mass m, which is represent as r prime. So we can know that we have theta here, so this gives us the horizontal component for our radius, which is r prime is actually equals to r cos theta. So this is our r cos theta here. Okay, so alright, so we know that okay, so we know that wait, let me, okay, alright, okay, we know that the mass m is actually located as at the mass sorry, not mass, at r prime. So the mass m actually exert another gravitational force, gravitational field strength, which is g prime. Okay, as m at the position of r cos theta, hence it experience the gravitational acceleration, which is actually less than 9.81, as the mass m is located at different radius. Okay, so let me see. Alright, so when mass m is located at this position, so it will undergo circular motion here, which is undergoing circular motion as the Earth is rotating with angular velocity, which is omega. So this mass m will also rotating with its own circular motion. So the centripetal force for this mass m is actually equals to m r prime omega square. So this r prime will represent our r cos theta omega square. So we can see that there is actually three components three components of force acting on the mass m, or forces acting on m, which are r primes, which this one will be r prime, so this one not no no not r prime, sorry. What I mean is force. So this force here is actually equals to m r cos theta omega square. So okay, this one will be 1. So this one, the force here, which is acting towards the center of circle, which is the true gravitational field strength, um, or which is mg, which is the true gravitational force, and another component for the true gravitational force, which is mg prime, as it lies at this angle, so okay, so we have this three component here, three component of force, which is important for us. Okay, alright, let me erase this one. So let me erase this one, so this one as well. Okay, alright. Okay, so as we know that there are three components acting on these forces, acting on this mass. So which is the first force, which is pointing towards the middle of the earth, not the center, only the middle. Okay, so which is mr mr cos theta omega square. So another one here, okay, another one, which is which is the true gravitational force, which is acting on the object, okay, which is mg. And finally, another force if oops okay another force at where the latitude of the mass lies, which is mg prime. So this mg prime to be noted as the location, the latitude where the object M lies, as we refer from the diagram just now. So these three forces, actually can be, okay, let me erase this one. So these three forces actually can be represented in terms of the vector diagram. Okay, let me draw a vector diagram here. Oops. Okay, so this one will be our vector diagram. This one will be mr cos theta omega square. Okay, so this one will be our mg here. Okay, let me draw longer. So this one will be our mg prime. Okay, So this one is r cos theta omega square. So this one will be our mg prime here. So this one will be our mg. So how can we determine the, okay, this one will be our theta. So how can we determine the actual gravitational acceleration or gravitational field strength, which is the actual gravitational field strength exerted by the object, which is mass m. Okay, how can we find this g prime? And we know that g is actually 9.81. Okay, so at this latitude, which is theta, we have a different gravitational field strength, which is less than 9.81. Okay, so how we gonna find this one? Okay, let me erase this one. Okay, this one as well. Okay, as we refer to this triangle, from the mathematics formula, we have a cosine rule. Cosine rule, which states that c squared is actually equals to a squared plus b squared minus 2ac cos theta. So this is the formula which refer from the mathematics formula. Oops, this one should be b prime. B a squared plus b squared minus 2ab cos theta. So our c squared is actually mg prime square. So this one will be our mg square plus m r cos theta omega square. So this one is another square. So this one will be our 2 mg m r cos theta, okay, omega square. So another cos theta. So this is how we, okay, by simplifying, okay, so as we can see that the mass for here is square, and here is square as well, and this one square too, and this one coincidentally we have two mass which is square, so we can directly cancel out the mass m. So this one will be our g prime square. So this one will be our g square plus, okay, so this one will be our, okay, let me see for a while. Okay, r cos theta omega square minus 2gr cos square theta omega square. Alright, so we square root here. Okay, so this one will be our g plus r cos theta omega square. So this one will bracket 2. So 2gr cos 2 square. Okay, so this formula we still can, this formula actually can be simplified. Okay, oops, sorry, my bad. Can actually, wait, let me see for a while. Okay, let's let's just leave it there. Okay. All right. So this should be our final answer. Okay. So this is how we find the G prime, which is at the latitude theta, which is always less than 9.81, as it always lies before the surface of the Earth. Okay, so let me erase all this one. All right. So let me erase this one as well. Okay. Oops. There are still some thing here. Okay. Never mind. Let me erase this one all. Okay. So let me rewrite again at here, as this formula is important for our next part. Okay, G prime plus R cos theta omega squared minus 2GR cos squared theta omega squared. So let me recheck whether this equation is true or not. Okay, alright, yes, it is correct. Okay, so let me erase this one. Okay, so what if the mass, okay, let's say we have our Earth. Okay, so we know that this one will be our north, south, east, west. So let's say, what about if our mass M lies at N and lies at north or south? So north or south, we can say that the theta is actually equals to 90 degrees. Okay, so at 90 degrees or at north or south, so cos 90 degrees is actually equals to 0. So this one becomes 0 and this one will become 0. So what we left is actually G squared. So our G prime is actually equal to G when it lies at north or south. Okay, let us remove this one. Okay, so what if the okay, let me take this. Okay, what if our mass M lies at east or west? Okay, east or west, so our theta eventually will actually equals to 0 degree. So this 0 degree cos 0 degree is actually equals to 1. So this one will be our G square R omega square. Oops, this one should be square. Okay, this one will be our R omega square minus 2GR omega square. So this one can be simplifying further, which is G minus R omega square. So this is the final answer for G minus R omega square. Okay, as we can see that at east pole or the west pole, G is actually equal to G minus R omega square. So at the North Pole or South Pole, so G prime is actually equal to G. So we can conclude that so when the object at the North Pole or the South Pole, okay, the gravitational field strength is actually equals to 9.81. So at the West Pole or the East Pole, the gravitational field strength is actually less than 9.81. So we can conclude that when the gravitational field strength at the West Pole or the East Pole is actually less than the gravitational field strength which is at the North Pole or South Pole. So this is how we determine the gravitational field strength based on the latitude of the object lies on the Earth. Okay, I think we stop here for now, so we will proceed on the next video. Okay, so that's all. Thank you.